Some background information. I think it's important that we can have a foundation for understanding why water is important in terms of conservation. We can talk quality another day, but in terms of conservation, we use a lot of water to irrigate. The EPA is very aware of this. I'm on an EPA committee, and you know that they're aware, and we have a bit of a target on our back. We need to be good stewards, or we're going to be in trouble. Of course, it varies. We have bigger problems in the West typically, but it's a nationwide, worldwide problem in many areas, and we'll talk about that a little bit more. And we get periodic droughts all over the place. So this is interesting. Shane Evans, one of my former students, he's actually getting a graduate degree up at Utah State University, and he's working on irrigation. I'm going to show you some of his data, but he put together this slide. And, you know, this just kind of shows where the potential, where this is going. And, so what you're looking at here is on the y-axis. This is average predicted, average annual prediction, and then projected change in population. And you'll notice that these western states have, have the biggest concern. And so for us in Utah, this is a big deal, California, et cetera. But I would argue it's a big deal in Florida and other places too. So we'll show you some data on that here in a minute. It's the most irrigated crop in the country. Turfgrass is included as a crop by USDA. About 30 million acres of total turfgrass area in the United States. That's a lot. And you compare that to irrigated corn used for grain, it's about double. I mean, that's huge, right? Now, agriculture is still the biggest, the agricultural row crops, they still take up the most irrigation total, but turfgrass is big and it's growing. As we see, if we look at just Utah, Nevada, Idaho, and Arizona, we got about 13 trillion gallons of water used. About 20% of that is municipal and industrial. The rest of it is irrigation. The average American household uses about 1,200 liters per day, which is there's about nearly 4 liters in a gallon. I should have converted that for you. About 30% of that is outdoor use, according to EPA. So what does this mean? I mean, here's some reality. This is, if you look on the left, that's 1984. That's about the year I graduated from high school in 83. You've got Lake Mead. You can see the size of that compared to 2016 has shrunk dramatically. That's just one example that's very visual that you can see. You drive by, you can see the banks exposed because we're running our water out. The Ogallala Aquifer in Colorado, Kansas, Oklahoma, Nebraska, et cetera, Texas. You can see that we've got some places in that area where that aquifer has dropped greater than 50 meters, which is about 200 feet. That's a huge drop. You've got areas that, if we run out of that water, it's going to dramatically affect the price of food, et cetera. So that's a real big concern and worthy of our attention. Recent drought in California, a couple of just aerial photos showing some of the impact in turf spaces. We look at drought monitor. This is January 21 to 2014. Obviously, we see the West is the often the biggest concern in terms of drought. But here's another one. Here's in 2017. We've got some droughts in the east, so it's not something that we ignore when we cross over to the eastern United States. This is kind of interesting. This is just a little bit of an evaluation just in Colorado. Of course, this is affected by that Ogallala Aquifer, but they've got a tremendous amount of growth rate in Colorado, also related to grass, right? But not the different kind of grass that we're talking here today. But got a lot of folks moving to Colorado. They anticipate this many acre feet, nearly 500,000 acre feet of additional water needed for those folks. The total irrigated acres in that basin is about 1 million. In order to account for this, they have to take it from somewhere, And so they're taking it from agriculture. And so cities will buy up acres, and then they take the water rights for those acres and are using them for urban areas instead of with their row crops. So that's huge. That's a big deal. We're shrinking our ability to grow food. Now, thankfully, so far anyway, we've been able to, our yields continue to climb, and we've been able to prevent starvation. Obviously, we haven't had big mass starvation in the United States, but it's a concern. All right, a couple of examples of some water restrictions because of this. One in Salt Lake City near where I live, and one here near where we are at today. In Salt Lake City, they have depending on the stage of the drought, they'll have mandatory reductions. Now, this is for the city of Salt Lake, which manages a lot of property. And so for them, they have these water restrictions that they apply to themselves. 20% reduction collectively is what they're looking for. Not at every property, every spot, but collectively over the city, that's their goal. Recognize different water requirements for different turfs and uses, allowing more for sports fields, for example. As restrictions became tighter, restrictions got extended to the sports fields. Some fields had to address poor irrigation design, which was a big improvement. That alone allowed them to kind of start meeting their goals, just realizing that. The golf courses were particularly good at this. They were very proactive. They turned off the water in the roughs, and they managed their water and actually exceeded their requirement to drop 20%. The playability of the fields and the golf courses was maintained. In some places was maybe even improved. Turf areas not devoted to field play did receive less water, and some of those browned up in the summer. That was part of what was acceptable by there. Anyway, overall, very effective, very positive. One of the things that they would do is they would take a property and they would help assess it. They had some experts that would look at it. They would say, okay, this is what we're going to do, and we're going to put this plan into place, and allowed each of these managers, who may not have been irrigation experts, figured out a way to cut the water back. So that was a kind of a big win. Allowed them to save 20%, and that was easy. It was easy to do that. It wasn't a difficult thing. Here in Southwest, or near where we're at, we're not right there, but close. Southwest Florida Water Management District. They look at these various factors. They allowed variances, including sports fields. In order to get a variance, you had to describe your water source and use, including athletic fields, etc. Describe the reason for the request. And if you had to kind of prove that you were going to manage it well and have a smart controller, which we'll talk about, etc. Have options for alternate to restrictions, changing times of days, just managing irrigation well. And you had to submit a map and say, okay, we're going to water, this piece this day and this piece the next day, etc. So you had to essentially put a plan. So, and that was effective, and that was needed, and that was here in Florida where, it arguably rains a lot. So we've got water restrictions all over the United States, more and more common. We've got to be better at managing this irrigation. So I'm going to talk about some things today that are going to allow us to conserve the water and still have playable surfaces. I could also talk about, what happens when the water gets shut off? And for example, I consulted with some folks in California during the last drought, and it's like, okay, how do I suffer through a drought when it's extreme and still get by? I'm not going to really talk about that much today. If anybody's interested in that, I'm happy to talk to you more about, kind of what we can do nitrogen management-wise, et cetera, to get through those kinds of things. But today I'm going to focus on just what we ought to be doing anyway, whether you're in a drought or not. These are just good practices to give me healthy grass and good surfaces. So we'll talk about some of these things. Let's start off by talk about turf grass selection. Species makes a difference. Bermuda grass, in terms of my warm season grasses, is one of the best. Previous talk in this room was addressing using Bermuda grass in the north. We're actually beginning to look at Bermuda grass in our area. We're not in a transition zone. We're in a cool season, but I've had Bermuda grass plots for over a decade with no winter kill in my plots. And anyway, we're looking at possibly using Bermuda grass. Currently, it's against the law to use Bermuda grass in most of Utah. It's considered a noxious weed. They don't understand common versus hybrid Bermuda grass. But anyway, we have some challenges to overcome in order to make that happen. But our biggest reason for that is water conservation, is that can we use less water across our campus. Our campus is about 500 acres, more actually, but it's a lot. And so if we could do that, particularly in our highest visible places, sports fields, that would be helpful. In terms of our cool season grasses, and I actually meant to say, so sometimes we think, buffalo grass gets the press. A lot of folks talk, let's switch to buffalo grass. Buffalo grass is nasty. I hate that stuff. It looks terrible. It's like gray-green. I don't even know what that color is. But it's not a popular thing for me. Certainly not a sports turf, but even on somebody's lawn. But in my mind, if I'm not in too cold of a place, I think Bermuda grass is a much better option. And we can kind of take buffalo grass and put it away. In terms of cool season grasses, you'll notice our bluegrasses, which are really our dominant cool season sports turf, and our ryegrasses that are used also are some of our worst. That's the problem we have, particularly in the northern regions, is dealing with bluegrasses. But even that, even if I can't switch over to Bermuda grass, how do I grow bluegrass with less water? And in my opinion, I do a fair amount of consulting, and I can't think of a single example when I went in for an evaluation where I ended up saying, hey, you're not watering enough. I'm usually saying, we need to dial your water back, and here's how we're going to do it. And so we can do that even with bluegrass. All right, so we have these various evaluation programs that help us in terms of picking the right varieties. I'm not going to go through that today, but whether I'm doing bluegrass or Bermuda grass, I can try to find grasses that are going to do well with less water, and that's something that I ought to be paying attention to. Here's an example. This is from the Utah State NTEP trials. These are bluegrasses. Obviously, that one in the center, not doing so well under reduced irrigation. But look at the ones around it. they got some really nice-looking ones. This one looks great. So there's some options out there in terms of that. But we have to do our homework. We've got to balance everything else out in terms of what diseases might I have in that area, et cetera. But in my mind, that ought to be one of the first cuts, is does it do well under drought? All right, fertilizer. Let's talk about that for a minute. I've done a lot of water fertility interaction studies, trying to understand better how nitrogen impacts water use, and it's pretty big. The other nutrients, now obviously like potassium, for example, if I'm potassium deficient, and most of us aren't, usually that's another thing I'm telling you to dial back a little bit is your potassium. Potassium has a big impact on water relations, so I need to make sure that I have adequate potassium, but I don't really see these tremendous interactions with the other nutrients and water like I do nitrogen. Nitrogen's really the big ticket item, so we're going to kind of focus on that. So we did a little study. We've done a bunch of greenhouse and field studies. We're looking at all combinations of low, adequate, and excessive water and nitrogen, and how those two things interact with each other. So what you find here is that for both irrigation levels, increasing nitrogen rates increases evapotranspiration. So the more nitrogen you're using, you're going to lose more water. It didn't matter whether I was deficient in water or putting on a lot extra, it's increasing my evapotranspiration rates. Nitrogen management can be employed for water conservation. We can see that has an effect. If we look at biomass and how many clippings you're going to be pulling off, that's going to be a big impact. And so if I'm over fertilizing with nitrogen in particular, I'm increasing my evapotranspiration, I'm increasing my biomass, and I'm not necessarily increasing my greenness. This optimum level here actually gives me my best greenness. This will look good too, but I didn't need it, and most of us are far beyond where we need on our nitrogen. On average, I'd say you're putting on twice, 50% to 100% more nitrogen than you need, based on my interactions with folks. So it's important. We did this little case study that's kind of interesting where we sort of put everything together. Kentucky bluegrass, we use common irrigation practices. Utah State provided for us daily irrigation with the automatic sprinkler system. The irrigation volumes were 2 or more times what is required. And the way we came up with that was that's what Utahns do. The average Utahn puts on twice as much water as they need. And so we're basing this little case study on what people are doing. We also assess common fertilizer applications, putting on 6 pounds of nitrogen, etc. The data showed that each one of the following practices are known to impact the water use efficiency, the rooting depths, and the shoot biomass production. And so we essentially what we've done is we compared what the average Utahn did, and then we scientifically tried to back it off, looking at both nitrogen and water, which I think you have to do. If I'm overwatering my nitrogen study, I don't really have good data. And if I'm over fertilizing my water study, I don't really have good data. And we got a lot of data out there where those two things aren't, they're doing research on one and ignoring the other one, and typically overdoing it. So what we've done here is combine them both. All right? All right, so one thing is appropriate mowing height is important. The right frequency is also important. I need to, and usually my sports turf folks, we don't have that problem. We have a bigger problem with that with, the regular lawn. It's not getting mowed often enough, and sometimes gets mowed too short. If I can raise that height a little bit, if I can talk coaches into that, that's usually a good thing. I sometimes try to show them data on speed of athletes, because that's oftentimes what they think is that, I can run faster on shorter grass. That's not true. There's all kinds of data that shows that's not true. Nevertheless, our coaches, pretty much all coaches, want short grass. And there are some reasons to do that, especially if I'm going to be playing and it's going to be dewy or rainy. There are some advantages in terms of slippage. But having a proper mowing height. Avoiding scalping. It's one of the most important things that I can do. If I'm cutting off more than 35 to 40% of the shoot, what's happening is you just stop root growth for about 2 weeks while that plant is now trying to recover. And that's not good. That's not good for water management. It's not good for the health of my grass. So one of the reasons why we want to mow frequently enough is to avoid that very thing. Appropriate fertilization based on soil tests and sound science. And I argue a little bit with folks. I'm a believer in the data. I love the saying, "In God we trust, all others bring data." Because I get people all the time saying, this calcium product is the best thing, or this. And I'm like, great, let's put it to the test. And about 99% of the product trials that I do don't perform any better than our best management practices. 99%. That's a lot. We do a lot of product tests. Most of it's garbage. So 1%, we find some cool stuff. We got some really neat products out there, and I'm always open-minded. But it's, I'm going to base my stuff on the science. Now, we have dialed our nitrogen rates back considerably. My program, there's a couple of programs actually I'll talk about. I've listed one here, and I'm going to bring up another one too. But if I'm using a dry product, if that's kind of the way I want to do it, kind of the low maintenance version of nitrogen management, I like to see a polymer-coated urea, I'm not supposed to say product names, I almost slipped. So A polymer-coated urea, if you would like, you can go search the literature and see what things I've done research on, and you can see what things work well, because not all of them work well. I like about 2/3 of my mix as polymer-coated urea, and about the rest of it as ammonium sulfate. I like that mix. It gives me a little shot of quick-release nitrogen from the ammonium sulfate. Most places I'm dealing with need sulfur, and so I get a little bit of sulfur out of that. If I have high sulfur in my soil or my water, I would substitute urea instead of ammonium sulfate. It's cheaper, but normally I'm putting on this blend. And I'm somewhere, even with sports turf, even with sand, I'm somewhere between 2 and 4 pounds of nitrogen annually, with most of it going on in the fall. So I'll hit it, and I'm usually doing 2 applications, and that's enough. Now, if you've got a bigger budget than that, fine, we can talk about that. But we've got data saying, well, 3 applications wasn't any better than 2 applications. That polymer-coated urea will get me through the summer. The notion that it's 1 app, and we get some products called 1 app, meaning 1 application will do me for the whole year, which is really nice if I'm dealing with a school system. I got a low-budget operation. I got to really watch my pennies. That's tempting to say, hey, I can put in my fertilizer down once and I'm done. It doesn't work. But we found that 2 applications does work. Fall and spring works great. Don't need 3 applications. It'll look just as good with 2. So that's where I'm at. And in that range of 2 to 4, it depends on soil types. Obviously, if I'm sand, I've got a lot of water moving through, I probably need to be up more like 4. If I got a soil that doesn't drain as much, I'm probably closer down to 2, et cetera. How deep are my roots? Those are kinds of the questions that I sort of look at to decide where I'm at in that range. I probably would be reluctant to go 2 pounds with most sports fields, but I'm telling you, we've done 3 and been just fine with most sports fields. And I get people kind of arguing with me a little bit on that, but again, the data is the data. All right, develop deeper roots. That's your mechanism of obtaining those nutrients, is getting those roots. And if my roots are super shallow, I've got a problem. I need to get those down. Cut the nitrogen rate. We have found that excess nitrogen is one of the biggest reasons why we have short roots. We like to talk about mowing being the biggest reason. Definitely mowing height affects root depth. The shorter you mow, the shallower your roots. But we're mowing at about 3/4 of an inch at Lavelle Edwards Stadium, and not my choice, by the way, but we're mowing about 3/4, and we have roots down at 8 inches. So that's great. You don't have to, don't tell me that short mowing is going to limit my root system. I think if I'm managing everything else right, I can still have reasonably deep roots. Number 1 is to cut the nitrogen rate. Plenty of fall nutrition, especially in the cool season zone. That's when plants are making roots. Brad.
So then, like ample fall nutrition, like if you were going to break it down into percentage, like 75% in the fall, 25% the rest of the year, so 63, 63, 33%?
Yeah, that's a great question. The question is what's the breakdown fall versus spring? I don't have good data to say. I haven't actually looked at that. Other people have, and there's kind of a mixed bag. But I'm where I do and it works is 2/3, 1/3. Now it might be better at 75, 25. I don't know, but I'm just slightly heavier in the fall. So for example, let's say I have 3 pounds that's going on over the year. I'll put 1 pound on in the spring, and I'll put 2 pounds on in the fall. That's sort of my easy to remember formula, and it works. It works pretty well. But I need that nitrogen throughout the fall. The problem we have is most of us, especially homeowners, not so much you guys, but most people, they're excited. Spring's, ready to get out and mow and do whatever, and people pay attention and fertilize in the spring. Most of us in the world don't fertilize in the fall. And most systems are nitrogen depleted in the fall, especially the late fall. And when do I need that nitrogen? When your mowing is slowing down, that's really the most important time for nitrogen. Is when I'm slowing down, I don't have as much shoot growth happening, and my plants are now making roots. It's like, hey, it's time for winter. Time to grow deep. So I can make a lot of inroads by going in that direction. All right. I intentionally stress my grass at least twice during the spring. I don't do it in the summer when the heat of the battle, but I don't turn on my irrigation system in Utah. We'll have people turn on the irrigation system in March. It's raining and the irrigation system's running, and you've seen all that, right? I'm oftentimes not turning on my system until May. I wait. My wife loves this, by the way. I wait till the grass doesn't look very good. It's kind of a little bit gray. You step on it, it doesn't pop up. It's drought stressed. Now, in sports fields, sometimes I can't do that. If you're playing every week and it's got to be looking good all through the spring, you might not be able to do that. But ideally, you want to get an intentional stress early in the spring. And what happens is, and it's a little bit hard because I'll have to go out and hand water because I'll get this spot right here that'll go a little drouthy on me, and I'm still green over here. And so it takes a little bit of extra effort. I got to go out and kind of hand water this one so it doesn't get too drouthy on me. But ideally, that's what you want to do. If I can intentionally stress that to where it's visibly stressed, what happens is hormonally that plant says, I got to grow deeper roots. And that's what it does. There's a measurable difference in rooting depth. Brad?
Actually, this is very effective. We do that at Beaver Stadium, the football stadium, and that's been really effective for them out there.
Yeah.
I totally agree with that.
Good, thank you. Appreciate that. All right. And then, of course, deeper. We hear this a lot, deeper and less frequent irrigation. You want to kind of push that water down to at least the bottom of the root zone. You want to be careful not to leach. We don't want to leach our pesticides and our fertilizers below that root zone. So we don't go too crazy with how deeply we go. But for example, I just typically when I'm coming in and helping somebody, oftentimes they're watering every day, oftentimes multiple times a day. Like if I go and talk to my neighbor who's got some kind of automatic sprinkler system that has been running the same way since the day they bought the house, it's like 3 times a day every day. And you can't do that. It's just not healthy for the grass to do that. For one thing, we'll talk about oxygen. It just depletes the roots of oxygen. So don't do that. It needs to dry down a little bit between. The other thing that helps with is disease. I'll get less disease if I'll stop doing that. So pay attention to those principles. All right. And think about your roots, right? We talk about crops and native plants, and typically we've got very deep roots and different types of architecture and structure. And then here's turf, that little short guy right there. I frequently will go out on sports turf golf courses, and I pull up a sample. It's one of the first things I do when I walk out there, and it's not uncommon to see 1-inch, 2-inch, maybe 3-inch roots. And in my mind, if that's how short my roots are, that's a fail. That's not acceptable. So I want to grow deeper roots. I want to figure out how I got to do that. And it might be oftentimes oxygen deficiency, et cetera. And so water management and those things all are going to affect that rooting depth and nitrogen management. And I need to realize that it changes by the time of the year, right? You've probably seen this graph. I just always like to point that out. So when I say, we have 8-inch roots at LaVell Edwards Stadium, well, that's not in August. So, but we do get roots down that deep. By August, they might be 4 inches deep as they've kind of shrink up a little bit through the course of the season. All right. Any questions about any of that? Yeah. Yeah, so I typically am doing 2/3, 1/3. We do have data on that, on the percentages, and we feel like that's a really nice percentage. Is 2/3 of a control release and 1/3 of a quick release. I think you can go on one side or the other of that and probably be okay, right? Oh, I forgot to mention, I said I was going to say this and I didn't. Kind of a higher end approach to fertilization, if I have the budget, and it's really better. I'm a big fan of polymer-coated urea. But if I can spray my fertilizer, I get a better coverage. Not only do we need to think about the depth of rooting, but we need to think about the cylinder of a root, of a single plant, especially if we're talking Kentucky bluegrass. Not so much Bermuda grass, But perennial rye and bluegrass have a very narrow cylinder. And so when you go out there and you fertilize, especially if I'm putting on a pound of nitrogen per 1,000 square feet, some plants are getting nitrogen and some aren't. We have data that shows that. Now, over a course of time, it kind of works itself out. It oftentimes, especially on a new sod or new seed, you'll see that spottiness with granular fertilizer. So I get a little bit better coverage if I spray that. And I can apply that, if you want to go put it on every week, that's fine. But I can do the same things I just talked about. I can do 2 apps. But again, I have to use a slow-release fertilizer. The problem is, I don't have enough time to cover this today in full, but a lot of times those liquids are going to release more quickly than the controlled release. So 2 applications makes me a little nervous, and I usually don't do that. And the other thing is I'm usually putting on some other pesticides, and so I'll look at your pesticide program and just slip some fertilizer in and kind of spread it out over the course of the season. It's a nice approach, a little bit better, more of a Cadillac, a little more expensive. Equipment's more expensive. Usually the liquid fertilizer is a little more expensive, but it's a nice. I get better uniformity by doing this. Okay. Oh, see, I had another question in the back.
Yeah, I was just going to ask, is it deeper time to try and get your roots? Do you use any sort of surfactants or anything to try to draw that water?
I thought about trying to include surfactants, and I just didn't have enough time to do this. But if I have problems, absolutely, right? If I've got issues with localized dry spot, then yeah. But it kind of depends on the property. So, but it's certainly if that's an issue, getting uniform water in the ground is also going to affect my fertilizer. It's a great comment. All right, let's talk a little bit about distribution uniformity. I'm going to kind of blow through this because I think most of us understand this, but if you don't, this is one of the most important things that we have to talk about here is I need to make sure that I get good coverage. We've all seen this, right? I'm pretty sure when I walk up to that spot, that's where my sprinkler head is, and I don't have the right pressure, I don't have the right package in place, or I've got a malfunctioning system in some way. So we do, and I'm not going to talk about how to measure distribution uniformity. You can Google that; it's pretty easy. You just go out there and collect a bunch of cups, and there's little calculators online that you can use to measure distribution uniformity. But if my distribution uniformity is only 50%, for example, which is pretty common, you're putting on way too much water. You're getting, 4, 5, 6 times as much water in some places than in other places. And that's a huge waste of water. And plus, that's not good for my grass. I'm getting some areas that are just too wet. This is pretty typical. This is 50%. I've got total yearly application ranging from 12 inches up in the upper left to 42 inches. So a realistic, some data there. You go in and fix it, this is another one that's even worse. That's huge, 30 inches versus 105 inches. I don't need 105 inches to grow grass. This is distribution uniformity, 85%. That's probably about as good as we can get. In fact, I don't ever measure. Even with the brand new system, everything's right. It's usually 80% if I'm lucky. But you can see a much better uniformity. But even with this, I'm still getting some, I've got 25 versus 36. It's still not perfect. And that's a reality that we're dealing with irrigation systems. All right. Yes, question?
I'm a huge advocate of uniformity in irrigation, but how do you translate that to efficiency? In other words, how much can you save? It's not the same thing, obviously. If it's 100% efficient, 100% uniform, but say 70%, how much water can you save by going to more uniform irrigation?
I think it's highly dependable on where you're at, right? The fact is that most of us are going to irrigate to that dry spot, and so that spot's going to get, if we're doing a good job, I'm going to be putting on just enough water in those drier areas. But so some of my areas are still going to be, not perfect. And so in terms of trying to put a number to it, I can't do that. It's going to be highly dependable on what your system is. All right. Now, I mentioned Shane previously. Shane's been looking at smart irrigation controllers. I'm not allowed to talk about various products, but he's looking at 4 specific controllers. You can go Google this and see it for yourself. I'm just going to talk about the principle that he's been able to discover in terms of using smart irrigation controllers. I think all of us would agree, this is a good idea. But the point I'm about ready to make is there's differences between controllers. So there's Shane. And a lot of folks on this project, huge project, cooperative with Utah State and BYU and others. So what he's done is he's got these little mini yards, right? He's not just looking at turf, he's also looking at the other plants. And so he's got these controllers and he's irrigating each one of these little square rectangular plots based on what the controller's telling him to do. And it's a completely randomized design, totally scientific, really cool little study. These are our objectives. Bottom line is we want to see which controller is working and how much water we might save in these particular situations. I'm not going to show you all the data. He's got tons of data. Stay tuned. It's going to be published. He's wrapping up. But this is just one measure. NDVI is a good measure of its normalized difference vegetative index. It's an indicator of plant health, okay? And we've got the 4 different controllers, and I've hidden the names for you. But you'll see that, with 2 of them, 0.7, that's pretty good. They're doing pretty well. These other 2, through the course of the season, we're getting a little too dry. It's actually starting to affect things. Now, philosophically, you could argue, well, maybe that's what we need. If I'm an extremist and I really want to conserve water and I don't mind my grass being a little bit less green or a little brown, then maybe I'm okay with those dropping off a little bit. But if I'm a sports turf manager, I probably don't want that. I probably want to keep those NDVI values up higher. And we're just using manufacturer recommendations on these controllers. You'll see, and again, I've blotted them out, but the 4 different ones, you can definitely see week 38, there's a difference across there in terms of what the grass looked like from an aerial view from a drone. So our conclusion were, first of all, we did have significant differences scientifically between the controllers and the water use. We also found differences in terms of soil moisture, percent green cover, and NDVI, and I didn't show you that data. There's lots of room for error with at least a couple of these controllers in terms of how you set it up. Compared to the average homeowner, though, all of the controllers saved water. So that's good news, and that's one of the reasons, even if you get one of the lower performing controllers, that's probably something we ought to be doing. The average Utahn puts on 1,200 millimeters of water a year. 2 of the controllers saved about 1/4 of that, and 2 of the controllers saved about half of that. And again, that was probably a little too much because they started tanking on us in terms of how they looked. All right. That's all I probably want to say about those smart controllers, but that's one of the things that we need to be doing is using smart controllers in our irrigation, but also looking at the data and saying, okay, not just trusting what we're told on a website or by a salesperson. We need to look at how do I save water most efficiently by selecting the right products. So I would encourage you to do that and take a look at that. All right. You've heard me mention oxygen a couple of times. My opinion, I think it's one of the most underappreciated problems that we have. It's frequently an issue. If you're overwatering, what's really the problem? Other than, I mentioned leaching. I'm going to leach my nutrients, leach my pesticides. But if I'm overwatering, is too much water what's hurting my plants? No. I grow plants hydroponically. I have all kinds of hydroponic studies. The roots are literally bathing in a solution of water. So how can I do that? Well, I have a little bubbler in there because I have to have oxygen in that root system. So too much water in a compacted soil isn't necessarily bad from the water standpoint, other than maybe, again, the leaching. But the problem is oxygen. It's oxygen depletion. And plant roots need good oxygen. And they won't go deep if it's oxygen depleted down low. And that's oftentimes one of the main reasons why your roots aren't growing deep, is there's not enough oxygen down deep. We're oftentimes dealing with compaction or focus mostly on the surface, and it's not uncommon to have a problem down deep. Now, you may or may not be able to fix that. We have some deep tine aeration that we do, and when we need to, it helps a lot. But certainly I need to be paying attention to that, and that's one of the questions that needs to be asked, is what does my oxygen do? So I need to aerate, and I need to irrigate properly, and doing it deeply and infrequently, that's the answer. I mean, it's not any more complicated than that. I just need to stop watering too often, and I need to make sure I got good aeration in my soils, which is hard. It's hard in these constructed soils. Okay, I'm just going to show you another little data, not a lot, but kind of interesting. We're getting more and more automated, right? Our homes are more automated. I got broken into the other day, my house, and my system that my son sold me, because he works for one of these companies, it worked. It actually worked. It scared the burglars away. They walked in, and the alarm went off, and they ran. But we can control our temperature of our house. We can turn on the coffee pot, or whatever you want to do happens. Those kinds of things are out there. But the same kind of thing in home automation is happening all around us. And the science is really pushing us. And so I'm going to talk about water sensors now. There are some new things that are happening that is worth our time to talk about today. One of the things, and this is complicated, so I'm going to try to make it simple in a few minutes. But in the laboratory, we measure soil moisture release curves. And it's really the most accurate way of measuring the moisture in a soil, is this kind of a thing. And what you're looking at is this relationship between volumetric water content on the y-axis compared to matrix potential. Now, volumetric water content is probably, if you've measured moisture in your soil, you've probably measured volumetric water content. But matrix potential is more accurate. It's not subjected to differences in texture, for example. So what I'm looking at here is in this particular range of the matrix potential, I have free draining water. Water is that's my saturation. Water is going to leave the soil freely. I have this section down to about 400 kilopascals, negative 400 kilopascals. That's where my plant available water is. Below that, if I start getting a matrix potential down here below about 400, minus 400, I have water there, but it's not available to plants. And so one of the problems we really have is measuring that. In agriculture, it's not as difficult because I've got these deep root systems, and I'm struggling with water, but I've got a little more air in the system. In turfgrass, I've got these really shallow root systems, and oftentimes we're growing on sand. And we have a really hard time getting accurate readings with sand. That was good. You guys all missed that, but it was funny. All right. So here's kind of my point there of my free draining water. And here is my, ignore this guy for the moment, but if I look at this soil, this is a soil and this is a different soil. That space up in there is my plant available water defined by those two arrows. Okay? A different soil will have more capacity. So we know that, right? I mean, some clay soil is going to hold more water than a sand. All right. So again, we do these. We typically have been doing these in the lab. We can study it. We get real precise, but it's hard to do it in the field. So we've been looking at, can we do this in the field? And I'm going to jump ahead. I'm actually not going to talk about this for a minute. So here's a plot next to our greenhouses. You can see some grass there. It's pretty drouthy. We've been studying drought and trying to figure this stuff out and how do we tell if a system's about ready to fail. This plot is really sandy. It's an ASTM spec sand that's identical to what we have in our football stadium. And man, there's just not much room for for error. I mean, the difference between having enough water and being in trouble is really narrow on this sand, which is common for sand. And we want a sensor that would tell us, okay, now it's time to water. And we haven't been good at that, frankly, for a long time. Again, if I have a regular soil deep crop, there's more forgiveness. I can get away with that. Sports fields is just one of the worst possible situations to try to manage water. So we did this little study, kind of cool. We buried a whole bunch of different kinds of sensors. I'm just going to kind of blow through this quickly. Now, we're going to look at a graph here. And I've blocked off most of the graph for the moment because it's just overwhelming. And you'll just, like, your eyes will roll in the back of your head if you saw this whole graph because there's so much to it. So I'm going to walk you through it really slowly. First of all, again, most soil moisture sensors measure volumetric water content. I'm showing that over there on the left, on the y-axis on the left, okay? Now, again, the matrix potential is the one that's not sensitive to. So we have better luck measuring moisture in sand, especially in sands, with this matrix potential. And so for this graph, we're going to use both volumetric and the matrix potential. You're going to see them both. So over here, this was during 1 year of this study in 2015. This is in June. You're going to see that I've got these waves happening. And that's every time one of those spikes, that's an irrigation, basically. Calendar-based irrigation. This is what we kind of always done. And trying to see, well, are we doing this right? I mean, we're seeing differences. So it's drying down between. I mean, the data says it's drying down. But wait a minute, maybe not so fast here. So those two are the shallow sensors at 2 and 6 inches. I've also got a sensor down there at 12 inches. And all of that is volumetric water content that you're looking at. And so we're seeing spikes every day. That's the point. That's the thing I want you to look at. Okay? Now, that's the matrix potential. They're flatlined, both of them. So what's that telling me? So although the volumetric sensors were telling us there were differences, the matrix potential is saying, no, you're saturated all the time. We are oxygen depleted in this particular field, and that's what that matrix potential sensor is telling me. So it's an improvement in the technology that's really new, and I'm really excited about it, actually. I think there's so much to learn yet, but it's commercialized right now. I mean, you can get this stuff. All right, so we started using the matrix potential sensors later in the season. I'm showing you the rest of the graph now. We started saying, okay, let's start trusting those matrix potential sensors and make sure that we're drying down. Again, what did I tell you on that matrix? It was about minus 300 or 400 kilopascals. That's when a plant's starting to run out of water. So we started watching it and irrigating when we hit that point. And I think that's where we want to go. We want to get to the point where we're actually measuring matrix potential and we're saying, okay, when am I dry? And that's when I'm going to turn on the water, is right then. And you'll notice that we had that all of a sudden up there at the top, we're seeing actual dry downs now. So you can see like that one right there is about minus 300 kilopascals. And so it's saying it's time to turn on the water. Now, one of the challenges of this is I can only bury these in a few spots. I mean, every one of these sensors costs money, so you don't necessarily want to, have them everywhere. So you got to kind of know your field, know where the dry spots are, and probably that's where we want to, get the irrigation fixed as best we can, and then install sensors in both the wet spots and the dry spots, so we can kind of see, when is the time to turn on the irrigation? Are we oxygen depleted in any part of this field? All right. Now just ignore this. This was us doing drought studies. You don't want to do that. You don't want to go that low. All right. The bottom line is we found some good results. We're excited about this data. Stay tuned. Again, if you're interested in that, something you can, I'll point you to it if you get a hold of me. Point you to this data. We're still trying to find our way a little bit, but I feel good. I mean, we're using this to irrigate now and feeling like it's a great thing. Any questions about any of that? Yes.
If you determined your volumetric moisture at the point of wilt, and then you use that as your set point, when you irrigate, could volumetric how you just applied it?
So that's basically what we were doing here. And that's what we've always believed. And that works in most soils and for most species, is to use volumetric water content. I mean, I've used these sensors my whole life, and I've done so effectively. But I've always struggled in sands. I've always struggled in especially pure sands. It's just they fail. The failure rate's pretty high with volumetric water content in sand, and so and also with the shallow root system. So, in my opinion, the matrix potential overcomes those failures. Other questions? I got a couple minutes, maybe. Yes.
What depth did you vary your sensor?
So, we kind of tried all kinds of things. I'll typically put them in like a 2 or 3 because that's where most of my roots are. That's probably, if I only had one sensor, that's where I'd put it. I've also put them down at 6, and then I kind of like to see what's happening down deeper too. We had them down at 12 just to see if we were leaching, and you can see, potentially we were leaching. And so it kind of depends on your goal. But if I had to have 2, I'd probably put one at like 2 or 3 inches and one just below the root zone. And they're not cheap, so these things are, not free. Other questions? Well, let me just say in conclusion then, one of the answers that gets bantied about by some is to just get rid of grass. And although I think there's an argument to be made that we could have less grass in certain spaces, we certainly see a lot of benefits from grass. But we've got to start managing the environment better, or we're going to lose our opportunities to have grass. We've got to start conserving water. Grass, though, can affect our heat signatures, and that's important. I mean, heat affects our energy, heating, cooling costs, etc. We get surface temperatures here's green grass, maximum daily temperatures. When I have grass there versus bare soil or even dormant grass is huge, and that can affect things. We talk about carbon sequestration. Climate change is a huge thing in the news. I don't know where you stand on that, but it's massive. People are thinking about that. And one of the best benefits of grass is it stores a lot of carbon. It takes a lot of carbon you're breathing out right now, and it pulls it into the soil and puts it in the soil. Grass is one of our most efficient group of plants that will do that. So there's a lot of reasons for us to do this. We all these home lawns out there are a big carbon sequestration machine. It's good to maybe even have these talking points as we try to justify our space. All right, I'm done. Thank you very much.